Hi everyone, I'm Ruffell. I'm going to give my talk, The Story of the Uncrackable Lockbox and Why Hackers Need to Work Alongside Developers. We're going to talk about a program called TimeLock. It's a homemade encryption program made by Kawaiicon of algomachines.com. What's interesting is that it implements a time-sensitive lock. So basically you have a time range which the lockbox will be available within. If you try and access it outside that range, you should be rejected. In order to test its security, its creator posted challenges to Reddit. Now, these challenges are a form of a lockbox, which is an encrypted file, and they contain a 0.02 Bitcoin private key as a reward. So in this talk, we're going to cover 5 simple vulnerabilities. They're relatively generic and can be copied over to other programs as well, so hope you enjoy it. So challenge number 1 was posted to Reddit in January. Kawaiicon claims that his program has an unhackable time lock, and the time is somehow synced to the Bitcoin network, and he offers 0.02 Bitcoin for anyone who gets in. So homemade encryption plus Bitcoin, I'm all over this, right? So looking at the website, we're given the password to this particular lockbox, which is TimeLock. There's a series of questions and answers which you get asked to ascertain that you're the right person for this lockbox. In this case, it's how much Bitcoin is in this lockbox, and it's 0.02. And we're given the time range, the start and end times, both in UTC. So the point of this engagement is just to attack the time lock mechanism only, not worrying about trying to break secrets or crypto or anything like that. So upon running the executable and trying to open the lockbox, we're faced with this prompt. 28 days, 1 hour, and so many seconds until the data is available. If you dump the strings in the binary, you see it appears in this form. And there's also another interesting string right next to it, which is select the folder where the file name will be created. If we can somehow figure out how to get from the first string into select the folder where the file name will be created, if we can figure out the logic path, we should be able to break this right open. If we check out the cross-references to days, hours, and seconds until the data is available, it's only used exactly once in the program, and we can jump to that location. It doesn't matter what this location does, but what matters is how we got here. So if we follow this red arrow upwards, we get to this junction. Now, we came up from this left-hand side. If you can see that call to time 64 at the top, there's a junction that comes off of that, just an if statement, and it's followed by a red line, so it's obviously the false path. There's a green line coming off of that, which is the true path, and we can speculate if we take the true path twice, we're probably going to be able to write the file disk. So if we have a look to the right and take that true path, it ends up to a string, select the folder where the file name will be written to, followed by calls immediately to fopen and fwrite. So we can speculate already this is post-decryption, and these are just some final checks just to see if you're allowed to open this lockbox or not. So it really means just the if statement, like the time lock mechanism is really just a pair of if statements, which isn't very good security-wise, right? So we could just patch it out. We can just change the conditional jumps to unconditional jumps, write this change to the binary, and run it. Remember everyone, just because something is compiled doesn't mean it can't be modified. In this case, shocked Pikachu for Kawaiicon. So we get loop number 1, which is pretty awesome. Yeah, magical internet money for days. I went and told Kawaiicon about this and said, why don't you use time as like a secret and pass it into the encryption function? So that's exactly what he did, and he issued challenge number 2. So we need a plan of attack for this one. Basically, we're going to try and track down where that time is passed into the decryption function, set it to the future if we can find it, see what happens. We know what the times are. We're given them as part of the challenge parameters. That was sometime in February. So basically, we can translate that to a Unix timestamp, and then we can change that to a hexadecimal number. Because as we're stepping through the program like a debugger, like instruction by instruction, if we keep an eye out on the registers, if we see those hexadecimal numbers come up, we can probably guess that's the current time, and we can swap it out from there. So if we try and decrypt the challenge binary, we see this prompt, incorrect answers, or the current time is not within the time lock window. Cool. If we check for cross-references, it's used in the program exactly once. So we can jump to that location like we did before, but of course, it doesn't matter what it does. What matters is how we got here. And we got here by this hunk of assembly at the top. Now, there's a call to this particular subroutine in the middle. If it returns true, then we go down to a file path where we write everything to disk. If it goes to false, we get to that prompt. So we'll figure out what this function does. We just open up a debugger, put breakpoints either side of it, and we notice that there's a buffer being passed into it. If we have a look at that buffer, there's a whole bunch of gobbledygook inside of it, which means it's encrypted content. But if we step over it, we get plain text. And this was just a lockbox that I had made myself with the time set 5 minutes to the future to try and understand what was going on. So I went and had a look at the encryption function, stepped through it instruction by instruction in my debugger, and I found this place where a memory location was getting dereferenced and a certain number is being loaded into RAX. And you can see it's 5C4, which is sort of like the numbers which we wanted to see before, right? If we convert this to decimal, it's a valid Unix timestamp. It was actually the current time which I was trying to crack this lockbox open. So we found where the time's being passed into the decryption function. At that point, I open up the challenge lockbox again. I set a breakpoint at the place where that memory address was being dereferenced, and basically we can just switch out the number in RAX to sometime in the future, but within that time lock window, right? We can go back to our initial set of breakpoints, and we can go and try and step over the decryption function. So here's the challenge lockbox in its encrypted form. We step over and we get plain text, which brings us to look number 2. Awesome, sparkles and magical internet money. So I went and wrote this up and told this to Kawaiicon, and he fought really, really, really hard, and he went and fixed it and came up with challenge number 3. So let's give this a go. Now, the plan of attack this time, we want to have some fun. And we know that time lock has to connect to the Bitcoin network somehow to get the time, right? So how about we just launch a cyber attack? Basically, we just flood the network with a whole bunch of malicious nodes. They behave exactly like legitimate nodes, but they have their time set to the future. We can then disable internet access in the virtual machine and then force time lock to connect to these local nodes, and hopefully it'll buy it and open right up. So for that, we have to figure out how time lock connects to the Bitcoin network. So if we try and open up the challenge lockbox, and we get a packet sniffer running in Wireshark, and it's doing a whole bunch of DNS requests. These DNS requests are kind of special because normally they only return 1 record, but in this case we're getting 20 to 30 records. In the Bitcoin world, a seed node is basically just a random list of nodes which particular DNS address has seen and that's been alive in the last half an hour or so. And TimeLock was connecting to 5 of these. These were hard-coded into the binary. So if we're going to full TimeLock to connect to our fake Bitcoin node, we're going to have to control DNS somehow. Thankfully, that's pretty easy. I just jumped on GitHub, downloaded a Python script which implements a DNS protocol. I set Windows to resolve DNS to a local server, and that worked wonderfully. The problem was it only returned 1 address instead of the 30, so I needed to convince TimeLock that we were a real seed node. To do that, I picked up the RFC for DNS, and it turns out that adding more records to a response packet is actually fairly straightforward. I just pseudo-randomly generated a whole bunch of addresses that started with 127 to point back to that local host. And we got a working seed node working pretty quickly. From there, you can just change the time on the Windows machine, disable time syncing, set the time to the future. I downloaded Bitcoin Core, fired it up, it was listening on the port, opened up TimeLock. TimeLock connects to the DNS server, which then pointed to the internal Bitcoin node, and we only got 5 of the 8 required connections. I was pretty gutted, but it kind of makes sense, right? There was only 5 hard-coded seed nodes that we were connecting to. So what do you do when you get stuck? You search for strings. There was a function called add seed node, which was pretty well documented, and I jumped to it. And it turns out there were 5 calls to this particular add seed node function in a row. So you can already speculate this is where those nodes are being added. So I thought, why don't we just do it again? If we execute right to the end of that block, modify the instruction pointer from the last bit, putting it back to the top again, and then running it through again, of course changing the strings, which the DNS addresses we're going to get to, we would have 10 seed nodes instead of the 5 which were hard-coded, which is greater than the 8 required, right? So I did exactly that. TimeLock went and connected to the fake DNS node, went to the Bitcoin Core, got the time, and we have loop number 3. Magical internet money! Woohoo! So I went and wrote this up to Kawaiicon, and he was very impressed. He went and hard-coded IP addresses instead of having DNS addresses, and he performed attestation on connected nodes by requesting the block headers of the blockchain which that node holds, and he then verifies all the hashes and that sort of stuff is correct and only takes the timestamp from the final block header. So this kind of made attacking the TimeLock functionality a bit hard, so we need to come up with a different plan of attack. Now, We know it's a homemade encryption program, right? So we'll have a look at the crypto. We'll just look for bad modes of encryption and weak encryption schemes. And there's this awesome quote by Bruce Shiner of, anyone from the most clueless amateur to the best cryptographer can create an algorithm that he himself can't break. On this slide, we're more on the clueless amateur part, but that's okay. Everyone has to start somewhere, right? But let's have a look, see if we can break the crypto. For that, we need to be able to figure out where the crypto actually is. I just looked for instances of like fopen, fwrite, and there's normally crypto functions smushed in between those. Once I tracked one down, I made a lockbox just with some dummy data set to all A's, and if you step over it, it gets gobbledygook, right? So we've obviously found where encryption happens. If we check it out, we find this block of assembly. You guys aren't going to be able to see that from here, but there's only two things that really matter. The first part is that the top bit generates a single byte key stream, and that's fed into the bottom bit, which XORs 1 byte of plain text with 1 byte of the key stream. Now, I did this several times, and if you use exactly the same inputs, like the same password, same question and answers, and the same time lock window, we got the same outputs. So the ciphertext was completely deterministic. But encryption is performed by XOR, right? So we can just decrypt it by XORing again. The key stream's exactly the same. So we have symmetric encryption, which isn't all that flash, but it's good for us. So let's exploit this. Basically, we can extract the ciphertext from the lockbox file, go to create a new lockbox. We're just full of dummy data, just all A's. What matters is that the length of the dummy data is exactly the same amount of bytes as what we extracted from the ciphertext. We can just do the old switcheroo, swap the dummy data for the ciphertext that we extracted, and then we run the encryption function and we get plain text, which brings us to loop number 4. And we get more sparkles and magical internet money. So I went and wrote this up and I mentioned this to Crypto Kawaiicon. I'm like, you can't roll with symmetric encryption, it's a bad idea. So he was like, okay, I'm going to fix this. Now, he went and did that, and we're going to check out his crypto again for the 5th challenge. And the crypto looks like this. There's no problem in computer science that can't be fixed by adding more layers of abstraction, right? So basically, he just put more layers of encryption on. We go from encryption round 1 into round 2 and into round 3. The encryption's pretty much the same, but just in reverse. We decrypt round 3 first, then into round 2, then into round 1, then into a verification routine. Now, I went and had a look at each of these stages. Rounds 1 and 3 are instruction for instruction the same as the encryption function we met in challenge number 4, which is great, right? It's vulnerable to symmetric encryption. We know how to defeat it. It's all good. What matters is the second round of encryption now. Having a look at it, again, it's going to be too small for everyone to see. It just does a whole bunch of shifts and multipliers and some strange calls to tan and square root. Encrypting a buffer twice, we get a whole bunch of gobbledygook, which means this is absolutely not symmetric, right? But I did a couple more trials using like the same password, same questions and answers, but varied the time. And the output was exactly the same. I got deterministic output, which means it's not reliant on time whatsoever. So I had a hunch that I was just going to be using hard-coded constants, so we could probably just peel off one layer at a time, and we'll do exactly that. So we can extract the ciphertext from the lockbox data. We can pass it into the 3rd round of encryption, do this symmetric encryption attack, strip that layer off, which will yield us the 2nd round ciphertext. From there, we can go decrypt a new lockbox, set the time to 5 minutes in the future or something like that, and from there, using the same passwords and the same questions and answers, we're going to be able to strip off that 2nd layer because it uses hard-coded constants, which gives us the ciphertext of the 1st round. We can perform the symmetric encryption attack, strip off that 1st layer, and we get plain text, which yields loop number 5. And we're swimming in magical internet money now. This is great. So I went and told Crypto Kawaiicon that you really can't nest flawed layers of encryption because each round's individually flawed. We can just strip off one layer at a time. You really should replace it with some sort of, public-private key scheme. But yeah, I hope you enjoyed that. Quick about me. I'm a sustaining engineer at Canonical. I normally fix gremlins in the Ubuntu kernel, but reverse engineering is just a fun hobby that I began not too long ago. If you're looking for something kawaii, you should check out a manga called Ubuntu. It's basically a good introduction to Linux, and it's very cute. Otherwise, if you're interested in the vulnerabilities in this talk, all the executables and lockbox binaries are on my blog. You can download them. You can try reverse engineer them, try to do those attacks yourself. If you get stuck, have a look at the write-ups. They'll get you to the next step. But otherwise, that's me. Thank you very much.